Take a look at this sequence. As n approaches infinity, 1 over n gets closer and closer to 0. It keeps on getting smaller. But we can't get 1 over n to equal 0 because there's no real number that we can set n as to get 1 divided by n to equal 0. So why do we say that 1 over n converges to 0? Intuitively, yes. As n approaches infinity, 1 over n approaches 0. But if I asked you to prove that, then how would you do it? Imagine we're playing a game. I tell you, you can give me any positive number, any number above 0, and I can guarantee you that there's a point in the sequence where beyond that point, all of the terms are lower than the number that you gave me. You can give me a really hard time by giving me a ridiculously small number, but that just means I'll have to go further into the sequence, and I will eventually find a point where everything beyond that is smaller than the number that you gave me. Because this works for any positive number, this is a solid definition of 1 over n converging to 0. You might think, well, I'm not allowed to pick 0, so how can 1 over n converge to 0? You can't pick 0, but you can pick any positive number. So you can pick a ridiculously small number, but then divide that by 2 to get an even smaller number, or divide it by 1,000,000, and I will still be able to find the tail end of the sequence where all of the terms beyond that are lower than your number. This is what we mean by converging to 0. Since we're in maths, let's assign variables to these different numbers. The small positive number that you come up with to challenge me, let's call that epsilon. And the point that I find in the sequence where everything beyond that is smaller than your epsilon, we'll call that point when n is equal to capital N. Now let's put this into words. So I'm going to say that for any epsilon greater than 0, so for any positive epsilon, there exists a point, capital N, in the sequence, where beyond this point, so when lowercase n is larger than this capital N, 1 over n is smaller than the epsilon value. This might seem really overwhelming now that we've added variables and made this into a long definition, but I promise you it's exactly the same concept as the game. It's you giving me an epsilon, any epsilon above 0, and I'm finding this capital N in the sequence where beyond that point, everything is lower than the epsilon value that you gave me. Since we're working with sequences, both of our n variables tend to be positive whole numbers. We don't tend to substitute decimals or negative numbers into sequences. We use counting numbers, also known as natural numbers, and this is just any positive whole number. So it's good maths etiquette in our definition to state that our capital N is going to be a positive whole number. So we're going to say that n belongs to the set of natural numbers. If we want to get really advanced, we can start adding symbols into our definition. So we can replace for any with this weird upside down A, and in maths language, this is just a symbol that means for any or for all. We can also replace there is with this backwards capital E, which basically just means there exists. It's a symbol that translates to there exists. Instead of saying that n belongs to the set of natural numbers, we can use these two symbols, one of which means belongs to, and then this weird capital N means the set of natural numbers. So we are literally just saying belongs to the set of natural numbers, but just using two symbols. This definition doesn't just work for our 1 over n sequence. It can work for many other sequences, even with limits that don't equal 0. 1 over n is a particularly nice sequence to work with because it converges to 0, so we can just say that eventually in the sequence these numbers are going to be lower than epsilon, and it just means that eventually the sequence will go to 0. If we want to work with another sequence that doesn't converge to 0, instead of just focusing on the sequence itself shrinking down to 0, we now need to focus on the difference between the sequence and its limit. If that difference shrinks to 0, we can say that the sequence converges to that limit. Technically, this is what we were doing for 1 over n, but since the difference between 1 over n and its limit is just 1 over n minus 0, we were just working with 1 over n as the difference, so we could just say, yes, eventually 1 over n shrinks to 0. So we're essentially saying that for any small positive number, we can find a point in the sequence where the difference between the sequence and its limit is less than epsilon, so the sequence eventually is less than epsilon away from its limit. Since epsilon is a positive number, we need the difference between the sequence and its limit to also be positive. If it was negative, then this statement would always be true. Of course, for any positive number, a negative difference will be lower than this positive number, so this definition becomes absolutely useless. The way we get around this is we take an absolute value of the difference between the sequence and its limit. This basically just means that we take the positive version of whatever this number is. So even if we've got a negative number, the absolute value basically just bins off the minus sign. And if it's positive anyway, then nothing changes. It's just a positive number. Now that we've made this definition general to any arbitrary sequence, we've now derived the official convergence definition. Let me tell you a secret. This is university level maths. So if you understand even a little bit of this, you're a genius. So how do we use this definition to prove convergence for a sequence? Let's take a more complicated sequence this time that doesn't converge to zero. We want to prove that this converges to its limit. First we say let epsilon be greater than zero. This means that beyond this statement, anything that we prove works for any positive epsilon, which is what we want. That's what the definition states. It states for any epsilon greater than zero. So we're going to start off by just saying, yes, our epsilon is any number greater than zero, so this works for all epsilon. The next step is to find the point in the sequence where beyond this point, the sequence is always less than epsilon away from its limit. This is the hardest part of the proof. This is when your actual maths will come in. It's where algebraic manipulation is needed, and it's the point where a lot of people might get stuck. The easiest way to do this is using inequalities, and I'll try not to lose you along the way because this might seem a bit complicated. Let's start by simplifying this expression. Since n is always a positive whole number, because that's all we ever substitute into this sequence, we can take away this absolute value. This expression is never going to be negative because n will never be negative. Now we can compare this to 4 over n, because n plus 2 is bigger than n, so dividing by n plus 2 results in a smaller number than dividing by n. So we have this inequality, and we want this to be smaller than epsilon. That's our whole goal, that's what the definition states. But if this is smaller than epsilon, then surely this is also smaller than epsilon. So for this to be less than epsilon, we need n to be larger than 4 over epsilon. This is just a simple rearrangement of this inequality. So we found our point in the sequence. No matter what epsilon is chosen, as long as you set n to be larger than 4 divided by epsilon, then 4 over n is smaller than epsilon. So then our difference is also automatically smaller than epsilon, and that's exactly what we wanted. So now we write in our proof, choose n to be larger than 4 divided by epsilon. The last part of our proof is to just show the inequality that we've just come up with. We say that for all n larger than capital N, our difference is equal to this, which is less than this, which we know is less than epsilon, because n is larger than 4 over epsilon. And this is the end of the proof. This is a pretty standard university level proof. I hope you enjoyed this brief introduction to the convergence of sequences. It can be a little tough to get your head around the concept, but the maths itself isn't actually too hard.